how to reduce like sort of unwanted eddy currents, right? And today now move to okay. So now, for example, this is the same way the eddy currents are described. For example, it says permanent mag between the poles. The block is made to oscillate with the same initial amplitude. Use energy conservation to explain why. Yes. I'm lagging? Obviously I am. So the thing is, with respect to energy conservation, we need to understand that the beam the kinetic energy was doing work against the opposing force of eddy currents formed due to rate of change of magnetic flux. Okay, and this energy converted to heat energy within the block. So you guys need to remember that. Okay. Let me know if you have a question. Hello, Javeria. And Saman. Right. Now going to the next. So this question, yeah, opposing force of eddy currents formed due to, yeah. That is because the currents will be formed in a direction to oppose the motion, right? That's why. That's the Lenz's law. Okay. Then this question you guys should do it on your own, because this is just the eddy one, and you can see why inductions take place, and then you need to use the energy conservation, same thing, and why it is like losing energy when the switch is on. So you should remember this, the same thing that you have to write here for 3 marks, so just remember that. Anyway, now the important thing is this part today that we're going to focus, and I plan to do paper question 2 of paper 5. Kartika, I'm sorry we're late on that. Okay. So anyway, what I want to tell you is that when induction takes place, right? So induction takes place because there is obviously current going on. So let's suppose there is a current, alternating current going on. So we have current like this. So the magnetic flux is generated because of that current. So magnetic flux and the current are both in phase, and obviously the linkage is done with the coil. That means that actually magnetic flux density, current and magnetic flux linkage are all of them are basically 0-degree phase difference, because they're all happening within that same interval of time. So you guys need to remember that. Okay, is it clear, everyone? Any questions? Now, however, we do understand that EMF, when you look at the formula really, we know that since EMF is directly proportional to minus, the minus sign basically indicates the Lenz's law here, which basically means that the EMF is induced in a certain direction which needs to oppose this change happening, right?
Sir, your voice is lagging a little bit.
Still lagging? That's not fair.
Yes, sir. Yes, sir, it's lagging and your voice is quite low.
And even my voice is quite low. Okay, that's not a good thing. Today my internet probably, I don't know, it's working, it's streaming fine. I don't know why is this happening. You might be correct, there might be a problem there. So is it okay now at least?
Right, sir, it's better now.
Okay, so I'm saying current, magnetic field density, and magnetic flux linkage. Okay, here I've written density, please correct it, it should be linkage. Alright, so in the PDF it's wrong. They're all in 0 degree phase difference because they're happening together. Is it clear? But because EMF is rate of change, so basically the gradient is this, which means the EMF is going to be something like this. So the reason is two things you got to remember. Graph of induced EMF will be the gradient of flux linkage. Okay, the other thing is that it will have opposite sign, and the reason is because of the Lenz's law, that it opposes the motion, that's why, or whatever change is happening. Do you guys get it? So just keep that in mind, and this will basically help you in determining a lot of things ahead. Okay, any questions now, everyone? Anything you'd like to know? Okay, so going on with this, so for example, this question is given to you, and we need to see that there is like two lines, and this is magnetic flux, and this distance which it moves from this point. Okay, there's 40 turns of the coil. Now it says the coil is moved at constant speed between point P and point where x is 3.0. Calculate the change in magnetic flux linkage of the coil. Okay, now 0 and 3, from point P, which is 0 and 3, so we need to find the change. How do we do this? We got to find the gradient. Okay, now go here, take this point, so this will be 3 and 3, and that's going to be a 0 and 5. It's 10 raised to minus 6 as well. Anyway, so the change will be 5 minus 3, 10 raised to minus 6 divided by 3, 0 minus 3. Can you guys please find this? What would be the answer?
So, we can convert centimeter to meter.
Yes, yes, sorry. So to multiply by 10 raised to minus 2 as well. What you get then?
6.67 times 10 raised to minus 5.
Okay. Now in the next part it says the EMFs induced in the coil is this much. Determine the speed of the coil. Okay, fine. So yeah, so we know that if you look at we have the magnetic flux linkage. Flux linkage is basically given by BAN over T. Do you guys understand this? You guys can hear me correctly, right? I'm a bit worried now because today you're right, my internet is like a bit sketchy.
I can hear you.
Okay, good. I thought I got disconnected. Oh no, this is so sad. Okay. All right. Now, so basically, we need the speed that is basically at which it is moving. We can definitely do that pretty easily. So, so you
So
guys,
the answer,
yeah,
what you first one, is not correct.
what is it? So correct? Why?
I don't know.
So we had to take it to 3 centimeter, right? This one. We did take the change in magnetic flux linkage of the coil. Oh, we took the change. I'm sorry. My bad. I took this is basically a change in magnetic flux. Well, that's alright. And there are 40 turns as well, you know. So multiply by 40 as well. Can you do that? Ratika?
So it's still not correct.
Still not correct? That's not fair. Why is it? Why is it not correct? Let me check again.
So why do we have to do 10 million steps for 1 walk?
I don't know. They are crazy sometimes. Again. So we took the values correctly, no Gatika? So we have 3 centimeter and 3. So we did 5 minus 3, right? And then we multiplied 10 raised to minus 6. Yes, sorry?
So why did we do radians?
Because it's asking us to change the flux linkage, you know. That's why we're doing this. And then we had to divide, like for 3 centimeters, we had to do 0 minus 3 and then 10 raised to minus 2. Because it was centimeter, we had to change it into meters. And then there are 40 turns in the coil, which they've written here somewhere. We'll multiply 40. Gatik, you're not getting the right answer, right? So it will be 2 times 10 raised to minus 4 divided by 3 times 40. Let me check. Two times 10 raised to power minus 4 divided by 3 and times 40. It should be 2.67 times 10 raised to power something. No?
Sir.
Oh no, I understand why.
Sir, can you hear me?
Yes, the video. Sorry, we don't have to do this.
The
Yes,
Fox
yes.
game says you just have to take 5
Yeah,
minus
yeah,
3
yeah.
times 10 to the power negative 6.
I
So
understand
you
why.
don't really care about the x.
No, we do care about the x. Basically, if you find the change, that would be equal to something else actually. We just need to find the change on this side, nothing else. We have flux already given. So that's why it is saying like that.
Yes.
Radhika, can you do this?
So when do we have to use that gradient formula?
When we have to find EMF.
So this is 8 times 10 raised to negative 5.
Negative 5?
That is the answer.
Okay, now it will be correct. Because they're just asking about the Weber's change here, not...
So why did you take the x-axis values?
Because it says Weber only. It doesn't say Weber over centimeter, that's why. Or Weber over meter. So I thought it was asking about the change in the line. It's just asking us to find the change in y-axis. You get it?
Yes, sir.
Okay. Now, this is the distance it has traveled. Distance is like 3 centimeters has traveled. Now it says this is the voltage. So voltage is given, and we just need time. Okay. So EMF is given by change in magnetic flux linkage over time. Okay. So we can find time. The change in magnetic flux linkage we found out to be 8.0 times 10 raised to minus 5 divided by EMF is 5.0 times 10 raised to minus 4. What you get?
0.16.
0.16 seconds. Now speed equals to distance over time. The distance was 3 centimeters, so 3 into 10 raised to minus 2, and time was 0.16. Can you find speed in meters per second then? 0.19 meters per second. Is that correct? Please check the answer. I'm not sure about that.
That's correct.
Okay, good. Now, the real question basically starts from here, where it says you've got to sketch EMF. Now, because this is like flux linkage and centimeter, right? So we got to do that. So we need to understand that within this section, if you look at the flux linkage here, you might realize that basically the change in flux linkage is this much. It is negative gradient. Everybody understand that? So when you're drawing this, you need to basically make EMF will be now positive and constant. So here I'm just gonna write few things so that you guys understand this. This line has negative gradient and it has a constant magnitude. How do I know this is a constant magnitude? Because in AS I've learned that a straight line has a constant gradient or constant magnitude. Do you guys understand this? Which means I have to draw a positive value till positive constant value of EMF till 3 like this, and then on the other side this line basically shows positive gradient and constant value, which means EMF is like negative of that, which means it will be a greater value because the gradient has a greater value in the negative side. Do you guys understand this? Like that. So remember, whatever you have here, whatever you get from this, the gradient of any of 3 graphs that I've told you will be EMF value, and whatever you have, whatever the sign of that gradient is, you just need to do it like, or you have to take an opposite sign in the graph of EMF. Any questions here? Please let me know. Suman and other people. Everybody get it? Okay, now let's practice it a bit more, okay? And the, I think next question is similar. So when looking at this question, it says magnetic flux linkage first of all. Okay, so magnetic flux linkage, basically just remember the formula. Oh my god. Okay, so we're writing the formula of magnetic flux linkage is BAN. Okay, so we're going to explain this only. So we're going to write magnetic flux linkage is equal to magnetic flux density times perpendicular area to field times the number of turns, and this will give you 2 marks. Writing perpendicular usually have 1 mark. Okay, is it clear everyone? Any question? Now check this out. Now again they have given you like you want to find the gradient, and from gradient this time we need to use EMF, right? So how do we find EMF? There would be some turns, so they have said 640 turns and diameter is this much. So area would be pi by 4 d square. So pi by 4 6.0 times 10 raised to minus 2. Can you find the area please first? What'd you get?
0.047.
Okay, meter square. Then what do you have? We need to basically find BAN. Okay, so we have the turns and we need to find the flux density. Okay, with
So d
respect
square the only meter. Was it d square, right?
d square. Yeah, oh sorry, did you square it?
So then the answer is 2.83 times 10 to the power of negative 3. Yeah. 83 times 10 to the power of negative 3.
This one? Okay, good. Now we're going to use, basically we want to find the EMF maximum amplitude. So the maximum would be when the gradient is the steepest, and the gradient steepest is this line, not this line. Do you guys understand this? So then what you're going to do is you're going to say EMF equals to minus change in flux linkage over time. The change in flux linkage will be minus B magnetic flux density. I don't know if that is given, but we can find the gradient of this by taking that. Doesn't really matter. So how do we do this? From this point to this point, you might see here it's sort of 1.2. So time is 1.2, and the flux change was 250 millitesla. So we're going to write 250 times 10 raised to minus 3 divided by 1.2. This will be B times the area. So what I'm doing is, let me just write it in detail here. So what I'm doing is I'm basically writing the formula is minus BAN over time. So B is this. A I found out, you guys found out to be this one, and N was like 540 I believe, yes, and time is 1.2. Can you find the voltage value? The change must be negative,
0.32.
0.32. Okay, that would be the answer. Is it clear everyone? Cool. Now we're gonna go forward. Okay, and this question is so good. So in this question it says sheet X is displaced from one side and released, so it oscillates the motion in the sensor used to record the displacement X. Fine. The second thin copper sheet Y is replaced sheet X. Sheet Y has the same overall dimensions as X but is cut into shape as shown, like you can see. The motion sensor is used again to record the displacement, the origin of the graph. The graph in the figure 9.5 shows the variation. Okay, fine. And now it says state the name of phenomena illustrated in reduction of amplitude. So obviously, when the reduction of amplitude takes place, this is basically damping. This comes from the oscillations chapter, and then it says phenomena should be light damping actually. Okay. And then say reduce the copper sheet represented by dashed line. Explain your answer. Reduce which copper sheet is represented. So dashed line will be represented by the whole sheet. The reason is that if the overall area is more, then there will be more, say, eddy currents that are going to be formed, and because of these cuts, the overall area reduces. That eddy currents will be reduced, which means that now there will be less opposition to the motion. Okay, so that's what we're going to write. So if I were you, I would write that second sheet has solid line and first one has dotted. So that's the first statement that will give me 1 mark. The second mark I'm going to write is that when sheet moves, it cuts the magnetic field, okay, causes a change in flux linkage per unit time, okay. Hence, the current is induced like that. Now come to Lenz's law. The current is induced in such a way, in such a direction, to oppose the change. You can also write the resistive force, okay, the force, the change or motion, by providing resistive force. Now, since area of the sheet, what sheet is that? Sheet X is more, hence greater current induced, and so the resistance is higher. Do you guys understand this? Okay, any questions now? Please let me know. Ahmed and Juveria and Aman, Muneeb, Gatika, Mokshit.
No, sir, I get it. Just I'm writing.
Mm-hmm. Okay, cool.
So the dotted one is sheet X, right?
Yes, obviously it is. Okay. Now, should I go forward now?
No, sir, I'm writing the fifth
Okay,
statement.
okay, you can write it down. No problem at all.
So what is the last word in statement 4?
Oppose the motion by providing resistive force.
Okay.
Okay, you guys, what do you say?
Alright, sir, I'm done.
Okay, cool. Now, this question is very similar, the same thing. I just want you guys to do it. But we're gonna move to this one. So it says the part B of this question, okay? Part A, you guys do it. It says the current is now this and show the variation of time reading. Now you see this is current and this is EMF. So we gotta understand whatever the gradient here is, we're gonna make the negative value, we're gonna put a negative of that value underneath, okay? So right now this one has positive gradient and the magnitude is constant. Magnitude is constant, okay? So that means that we have to put a negative line till t1 and constant value has to be constant for voltage. Is it clear? Now if you look at this part, this is not exactly a straight line, it is a slanted line. Slanted line means this has a negative gradient, obviously, and it is magnitude is constant, but the magnitude is larger than before, which means now negative means we're going to make a value which is higher. Like we can show it like a peak. Just make it a peak like this, okay? A peak, because it will quickly shift through this like this. All right, is it clear, everyone? In here, the gradient is 0. It means the peak will quickly come down and then it will stay 0 because the gradient above is 0. Do you guys understand this? Let me know.
So could you explain once again?
Again.
Sir, you can get the number above.
Yeah, I'll do it again, no problem. This is basically something that you guys need to draw, so it's okay if you ask me again and again. So from like this position, right? So this is like this position, just before T1. Do you guys agree this has a positive gradient? You agree?
Yeah.
Positive gradient means that EMF value has to be negative now. Do you understand? Because it's always opposite sign. And it is also constant in value, constant in magnitude, because it is a straight line, okay? So it means the gradient value, we have to put a negative value of EMF just before T1. Do you guys understand this? And straight line, like that. If you look at this line from start, like almost start of T1 till the end of T1, you might realize that this has a negative gradient. If it has a negative gradient, then the EMF value will be positive. And it is also constant. But the magnitude of this, because the gradient, if you look at this line, the slope and this, the slope is very different. This has a greater gradient, this is a smaller gradient. Do you understand? That means that the gradient is now going to shift on the other side as positive, but the time is so short, right? It's gonna go like this. So you can make a dotted line if you want to, dot it till here, and then shift it up, and then it becomes 0 here. How do I know it becomes 0? Because after this section has 0 gradient. It's a flat line. 0 gradient means 0 EMF induced. So till T2 it's like that. So if I put numbers on them, so this line is shown by 1, this 2, and this is 3. So this is 1, 2, 3. Do you guys understand? Look at this, please. Have a look and let me know if you understand this or not.
Sir, is there a reason why you made, when you were increasing the line, why did you make it dotted?
Just to show that it's going towards the other axis. You can make a solid line, it's alright. There's no particular reason for that. It's just that in this graph that I drew, I could have also drawn, where was that? I also put a dotted line just to show there was a change, but you can make a solid line as well. Okay?
Okay.
Sir,
Yes, Manip?
for the third part, could you explain that again?
The third portion here, this is the
Why-
third line.
Yeah, why did he put it at 0?
0, because if you try to find a gradient of flat line, the gradient is 0. There's no change. If the gradient is 0, then EMF will be 0 as well. So that means 0 here. You get it?
Okay,
Like that.
yes.
Okay, so the rest of it, obviously, you guys don't do. This is a very similar question.
Sir, so when you're drawing,
Yes?
sir,
Yes, it's very.
so when you're drawing the line again, the T1 is where you're gonna have the peak, right? Exactly above T1.
Yes, exactly. That's the middle of
Right.
it, that's why.
Okay.
Because I realized that basically it's the center and there is like, it will start just before T1 and ended just after T1. That's why I did it here.
Alright, sir.
Just before and after. Okay, is it clear? Alright. So then, this first part you guys are going to do. This is because the same question. Nothing really different, but I'm going to help you do this. And this time I'm going to ask you. So I'm going to put this as 3 different sections or different sections. So I'm going to call this 1, 2, 3, 4 and 5. Let's take these, okay? Now we also need to put the values, unfortunately. So, and we do not have that, unfortunately. So what do you do? And this is like 4 marks, so they want you to take the values out. First of all, we know EMF has to be minus BAN over time. You guys agree with this? Okay. Now, think about this. In the first section, which is the first one, what will be the gradient? Tell me, please.
0.
0.
Sir.
That means EMF
Zero.
will also be 0 till what time? Till 0.1. So can I put,
0.1.
yeah, can I put a line like this then? Okay.
Yeah, makes sense.
Then this one, you guys need to understand the gradient here is negative and it is constant as well. Agreed? All right. Now this section, how much? What is the change of B? The change in B is like, this would be 7.5, so 7.5 millitesla, right? So I'm going to put and find the value. So 7.5 times 10 raised to minus 3. The time between this change is from 0.1 till this, which is 2.5, right? So 2.5 minus 0.25. 0.25. Oh, I have to put time underneath. 0.25 minus 1.0.1. Sorry. Like that. So this will be time. I don't know if they've given area. Diameter is given, and we can just convert it to 1.2 times 10 raised to minus 2, okay? Radius. And say 160 turn. So 1.2 times, pi times 1.2 times 10 raised to minus 2 whole square. And the turns, the number of turns were 160. Okay. Can you find the EMF value here, please? What you get?
So before the formula it used was pi by 4 d squared.
Yeah, yeah. You can use pi by 4, 2.4 times 10 raised to minus 2 whole square, or pi 1.2 times 10 raised to minus 2 whole square. This is...
Oh, wait, okay. Alright, I got it. Sorry.
Okay.
Sorry.
Alright, it's fine. I'm just giving you another variation, that's fine. Okay. Anything? You guys find the answer, please?
3.6.
3.6. So, if the gradient was negative, so our EMF must be here positive. Do you guys understand? So, it means from this point to 0.25, you got to make a positive line of this value. So 3.6 would be 4.4, 4.8, sorry, 2.4, 2.8, and 3.2 and 3.6. So we're gonna make this line from here. Just make a dotted line here just to show that you've shifted up until this point. Okay, so that would be here. So a value like this. Do you guys understand this? Let me use a darker shade. That doesn't really resonate. Okay. Is it clear, everyone? Munib, Dipesh, and Mokshit, Gatika. Okay. What do you say about
Yes,
3?
yes, sir.
What do you say about 3? What is the gradient here?
0. 0.
0. So the EMF value will also be
0.
0. Till what point? Till from 2.0.25 till 3.5. Okay. So I'm gonna shift the line down back from 2. Oh, I made the wrong line. It should be somewhere in the middle, right here. Okay, so from here till 3.5 it should be 0. You guys understand this? So this is 1, this is 2, this is 3. So we have already done that. Then in this section, what is the gradient? Is this positive or negative?
Negative.
Negative. So it means EMF will be
Positive.
positive. Okay. Now let's find the change. The change is from this point to this point, which is basically 5.5. Okay. So let's.
5.5.
Sorry? Oh, sorry. 7.5. Isn't it the same value? I don't think so. It's the same value. Well, let's check it. Now, yeah. So 7.5 times 10 raised to minus 3 times pi 1.2 times 10 raised to minus 2 whole square multiplied by 160 turns, and the change in time was from this point to, I believe, this point. And what is
0.425 minus 0.35.
okay? What is that? You,
So isn't it 0.5? Okay, never mind.
I think the video is right. Yes, please go ahead.
7.2.
7.2. Okay, 7.2. So we're gonna go again to the positive side. We're gonna find 7.2. So it's 6.4, 6.8, 7.2 right here, which means till this point we're gonna go to just here, and it will continue till 4.25, right? 4.25 was this point, right? So I think, yeah. So just make a straight line. So this will be 1, 2, 3, 4. And then what about fifth? What is the gradient here?
0.
0. So EMF will be
0 to the EMF is also
0.
0.
So it means till the end, which is like 0.55, it will be just 0. Do you guys understand this? So this will be the graph for the graph above. Okay, any questions now? Ahmed, Rafe, Munib, Dipesh,
No, sir.
Mokshit, everything is clear? Okay. So I believe now you guys will be able to
Yes,
draw this, right? So this was the hardest, I think, that you can get. And for 4 marks, that's quite fair. And you have the same things, like everything is the same forward. So I'm just gonna give you this, the other things as homework so you can practice a bit, okay? And if you don't understand this, obviously you can come back and ask me, so that's fine. Anyway, so now I'm gonna basically put this as your homework, and we're gonna start with paper 5 question 2 today, okay? Let me put this as homework because I'm gonna forget it later, obviously. Dipesh, I didn't understand what he was saying. Yes, sorry?
When we're done, will you put this, your notes on the thing?
You want my notes? Should I send this to you?
No, when we're done the unit.
Yes, yes. Like the whole syllabus.
Okay. Yeah.
Okay, you can get that, don't worry. But you have to also put the assignments, so you should be making your own. But anyway. Restart. Okay. Alright, so I'm gonna now stop the recording and okay, so I'm gonna basically put like